Hi everyone, welcome back to another video. In this video, we are going to be discussing polarity of molecules and bonds. And before delving into polarity, we need to understand what is electronegativity. So electronegativity is the unequal attraction for shared electrons in any covalent bonds. So for example, right here, we have a hydrogen fluoride molecule. And if we draw the Lewis diagram, it's going to look like this, and the hydrogen atom and the fluorine atom will be sharing one pair of electrons. However, due to the difference in the numbers of protons in these two atoms, they will exert a different amount of force onto this shared electrons. Because as we know, protons are positive and electrons are negative, so they will simultaneously attract each other. However, since hydrogen has an atomic number of 1, which means it only has 1 protons, whereas fluorine has an atomic number of 9, which suggests that it has 9 protons, which means this fluorine atom will exert a much greater force on this shared electrons than this hydrogen atom, which means realistically, this pair of electrons will be closer to the fluorine atom rather than the hydrogen atom, which means that there is a electronegativity difference. And we can find the respective electronegativity grading for each atom on this table. We can see that the hydrogen atom has an electronegativity of 2.1, whereas fluorine has an electronegativity of 4.0, which means this hydrogen fluoride, this molecule, this single bond will be a bond dipole. And this simply means that the electrons will be closer to fluorine rather than to hydrogen. And on the fluorine side, we will have a negative dipole, and on the hydrogen side, we will have a positive dipole because all the negative electrons are closer to the fluorine atom rather than the hydrogen atom. So this is the concept of the polarity in a bond. And then, how can we determine if a bond is polar or nonpolar based on electronegativity? For example, if we have a hydrogen chloride molecule, and we know that if we draw the Lewis diagram, it will look something like this. They will share one pair of electrons, so it's a single bond. And then we go up to the table, and we can see that hydrogen has an electronegativity of 2.1, and chlorine has an electronegativity of 3.0. Now, we simply find the difference between the two numbers, and we will find 0.9. And as long as this difference in between the two electronegativities between the two atoms is not 0, it means there is a bond dipole. And we can see in the simulation, we can see that on the fluorine side, the electrons have a greater probability of staying on the fluorine side, whereas on the hydrogen side, the electron has a lesser density, which means it has a lesser probability of staying in the hydrogen realm, which means we will have a bond dipole towards the fluorine side. The electrons will be more likely to stick to the fluorine side rather than the hydrogen side. And we will have a partial charge on these two atoms as well. And now, what if we have a molecule? So let's say we have carbon dioxide. And as we know from our previous video on Lewis diagram, we will have the carbon as the middle, that's the central atom, and we will have the two oxygen atoms on both sides forming double bonds with the central carbon atom. And next, we want to decide whether these two double bonds are polar or nonpolar. So we can apply the same strategy by finding the respective electronegativity grading on these two atoms. So we would have carbon, which is 2.5, and oxygen, which is 3.5. So we would have 3.5 on the oxygen and 2.5 on the carbon atom. And we can find that the difference between these two electronegativities is 1.0. And the difference in electronegativities for these two, for this double bond, is also 1.0, which means that this oxygen atom has a higher capacity of pulling the electrons from the carbon. It can exert a higher force, a greater force on these two paired up electrons toward its own side, which means the electrons are more likely to stick to the oxygen on both sides rather than in the middle carbon. Therefore, we can deduce that on the two oxygen side, we would have a negative dipole because the electrons are sticking to both sides, while in the central carbon atom would have a positive dipole. Now, we have determined the bond dipole for this molecule, and we can use arrow to represent the likelihood of electrons. That's a good analogy to understand this. And now we want to find if we look at this molecule holistically, would it be a polar molecule or a nonpolar molecule? And the answer would be no, because these two bond dipoles will cancel out each other because it's on a linear plane. And we know that if we have two vectors on a linear plane and we add up together, it's going to be 0. Because the value on both sides is exactly the same. Therefore, if we look at the whole molecule together, it's going to be a nonpolar molecule. And a tip is always, if some molecules are symmetrical, and it's usually nonpolar. Other examples would be something like, but this symmetry must be on some sort of uniform plane. So let's take a look at water. And before we look at water, let's take a look at carbon dioxide. So we would have this as the molecule. And if we pull out the electron density, we would clearly see that the color are darker on both sides, which means that electrons are more likely to stay on the two sides. And this is also reflected from the electronegatividity grading here. The greater number means it has a greater capacity of pulling electrons to its own side. And if we look at the bonding dipole, we will see that we have two arrows pointing to two sides. However, if we look at molecule dipoles, we will see that this molecule has no molecular dipole, which means it is a nonpolar molecule. Now, let's look at water. So if we pull up the water molecule simulation right here, it's gonna be look like this. And as mentioned in our previous video, this is a angular shape or band shape. And let's analyze the bonding dipole first. So it would have an oxygen here, 2 hydrogen here, forming single bonds with 2 lone pairs on the central oxygen atom. And we will go find the respective electronegativity grading again. So the hydrogen is 2.1 and oxygen is 3.5. So for this single bond right here, we would have a difference of 1.4, and the electrons are going to be pulled towards the oxygen side. And the same happens to the other side as well. So we can see that the electrons are more likely to stick around this oxygen atom than these two hydrogen atom, which means if we look at this picture holistically, the electrons are more likely to stay on the above side rather than to the bottom 2 hydrogen atoms, which means this molecule will have a molecular dipole towards the oxygen side. And we can see this reflected right here. So we can see that the shading on the oxygen side is much darker than the 2 hydrogen sides, which shows how electrons are more likely to stick to the upper oxygen atom rather than the 2 hydrogen atoms on the bottom. And the 2 bonds are clearly polar, and they're all pointing towards the oxygen atom. And this is also could be calculated by finding the difference in the electronegativity gradings. And if we look at the molecular dipole, we can see that the electrons are more likely to stick into the upper oxygen atom, which gives the whole molecule a molecular dipole towards the oxygen. And that is the concept of the polarity of a molecule. So we can find the respective polarity for all these bonds, and then we can find we can determine using the holistic picture. Thank you for watching.